Hi class, welcome to section 2.7b, solving equations and inequalities both algebraically and graphically. We're going to go ahead and do in our warm-up here today, and I'll do it with you, is solve and graph the following inequalities algebraically. So to start, we've got 3x minus 5 is less than 7. Seems pretty routine. We're going to do things a little bit differently with our inequalities, which will set us up for the boundary algorithm on more complicated problems later. We're actually going to start off by subtracting 7 from both sides, which may seem counterintuitive since we can probably think about maybe adding 5 instead and then dividing by 3. But when we subtract 7, what we're setting us up for is setting it less than 0. And if you recall, when we did polynomial inequalities, we did want it to be set to 0. Which then, if you recall, we can set or make a note of two things in this regard where we want negative values because, again, it's less than 0. And because it's less than, we're going to have open values that are critical values. What we see here on the left is, in fact, factorable. In other words, we could factor out a 3, which leaves us with 3 quantity x minus 4. I'm going to set it equal to 0. That's what the boundary algorithm calls for. I'm going to jump right to my number line. And on my number line, I'll simply plot one point. I'm going to plot a point at 4. And that's going to be an open circle. Now, if you recall, because back when we said we wanted negative values, we're going to go ahead and use either our graphing calculator, although I think this problem is maybe easier than not in terms of using a calculator. I don't think we need it. So if I were to pick a number less than 4, I think 0 is perfectly easy. You can actually plug it in right here. You do want to use the test point in this particular inequality when you set it less than 0. So if you were to plug in a number less than 0, like 0 here, 3 times 0 is 0, minus 12 is negative 12. Is negative 12 less than 0? Yes. So all the values to the left of 4 are in fact solutions. As you may suspect already, though, any number to the right of 4 won't work, like, for example, 5. If we plug in 5 here, 3 times 5 is 15, minus 12 is 3, and that is not less than 0. So the answer to this particular problem, again, using the boundary algorithm appropriately, looks something like this. Negative infinity to 4 with a parentheses. Number 2, similar logic will be applied. I'll subtract 8x, and I'll add 7. So I'm setting up the course here for 4x plus 5 is greater than or equal to 0. From here, we note that we've got, again, our two things to highlight, particularly that because it's greater than or equal to 0, we want positive values. And the equal to speaks to the fact that we want closed values that are critical values. Okay, so we go ahead and, in this particular instance, I may just leave it as 4x plus 5, which isn't so bad. When I go ahead and simply take, well, I say 4x plus 5 equals 0, which leads us to a little bit more math, of course, subtracting 5 and dividing by 4. So my critical value will be at negative 5 over 4. It will be, as we noted from above, we noted that it was going to be closed, so I'll do that as such. So negative 5/4 is closed, as we see. Now, if I go ahead and I were to plug in a number like, gosh, let's plug in 0. 0 is really pretty simple to plug in here. 4 times 0 is 0, plus 5 is 5. And, of course, that is greater than or equal to 0. So every number to the right of negative 5/4 is a solution. As you could and should imagine here, any number to the left or less than negative 5/4 won't work. I'll pick a number like negative 2. 4 times negative 2 is negative 8. Negative 8 plus 5, negative 3, which is not greater than or equal to 0. So we write our final answer in interval notation. We say bracket at negative 5/4 to infinity, and that should be it. Let's move on. Problem number 3. In this instance, this is not an inequality, so I'll just go ahead and take a look at, again, using the boundary algorithm, subtracting 15 from both sides. Now this is going to be a little bit different. Negative 3x minus 22 equals 0. And then from here I'll say negative 3x equals 22, x equals negative 22 thirds. When we go ahead and put this on a number line, we say, of course, negative 22 thirds. It is only going to be closed at that value. And really that's the final answer. In interval notation, this will be it. Brackets with negative 22 thirds. So I'll go ahead and continue with example 4. Again, a little bit strange that I'm going to be splitting it up. If you guys recall, if back when in Algebra 1 and Algebra 2, when you did a problem like this, you didn't know about the boundary algorithm, you probably just, added 7, and then divided by 3, divided by 3. The idea, though, in this case is similar to the other 3 questions in that I want to set it to 0. I'll do that here on the first inequality, as you can see, because I've already split things up. I'll go ahead and just simply subtract 7, so it's 3x. Subtract 16, so it's 3x minus 23. I'll turn that into an equation, and then we can easily see then that x would be 23/3. Here, I'll do the same type of thing, where I will subtract 25, so I've got 3x minus 28 less than or equal to 0. Again, set this equal to 0, and then, of course, x is 28/3. Interestingly enough, yet again, we go to our number line, and then each individual inequality I can stress as kind of its own separate notation, in that the first here, because it's less than, technically as I'm reading it, it's 0 less than this, but we want this whole thing greater than 0, which tells us we want positive values. And because it's less than, not less than or equal to, technically greater than or equal to, we say open. Again, reading it from right to left. Similarly, though, in this case, because the quantity is, as you see, less than or equal to 0, we say that we want negative values. And secondly, closed. Okay, so we go to our number line, and we go ahead and identify both 23/3 and 28/3. Now what I'll go ahead and do is just see what 23/3 happens to be, as well as 28/3 as a decimal. Just give us some perspective. Okay, so 23/3 is about 7.6 repeating, and then, of course, 28/3 is 9.3 repeating, which I'll go ahead and jot down. Okay, so in this case, I will attempt to use the store feature. Using the store feature, I'll pick a number less than 7.6 repeating, let's say 0. So I'll go ahead and hit 0. Store is x. And I'll go ahead and I'll type in 3x minus 23 from this inequality that I initially had set up. So 3x minus 23. Now that answer, of course, is negative, right? And we said, again, looking at it, we wanted it to be positive, so we won't graph to the left of 23/3. We could pick a number like 8. Actually, 8 would be pretty smart in between the two. Now, it should be predictable that 8 will work, but let's go ahead and test that. 8 stores x, and then I'll just hit second enter, and I will actually not only test it with 3x minus 23, but I'll test it with 3x minus 28. We do that, and we hope for the result being, on that one, being negative. Okay, so this one was positive, this one was negative. So this is going to be graphed in between. And then last but not least, a number like 10 won't work, and I'm just going to test that here. So 10 times 3, is 30, minus 28 is 2, which is not less than or equal to 0. The answer in this particular instance is just 23/3, parentheses, 28/3 with a bracket. Moving on. We're going to take a look now at rational equations and solving them. In solving this rational equation, what we're going to go ahead and do is find what we call an LCD. Now, the LCD for this particular situation, or this equation that we're going to go ahead and define, partly will be thanks to the fact that the second fraction has an x, the third fraction has an x minus 2, and if we were to kind of off to the side here and look at the first denominator, we can notice here that it is factorable as this, x quantity x minus 2. So because the second and third fractions have both of those things, our full LCD is this. So when we go ahead then and try to figure out how to work with something of this nature, we go ahead and kind of rewrite the entire problem. Should be a plus sign. Rewrite the entire problem, but of course, now that we've got to consider the LCD as part of the process in solving this, we want our equations, we want our fractions to have the exact same denominator. We can't do anything with fractions otherwise. So I'm noting here already that I've got a fraction to be multiplied to 4 over x. And also on the other side of the equation, we'll do the same thing as such. Okay. So go ahead and, in terms of multiplying 4 over x by the quantity that will allow us to then have the official LCD, I'll say x minus 2, x minus 2. And on the other side of the equation with the other fraction, I'll simply write x over x. Now something really, really neat is going to happen here. If I were to multiply both sides by the LCD, it's going to actually cancel quite nicely. So what we're left then with is 10 plus 4x minus 8 equals 5x. In solving this, it's pretty straightforward. I can subtract 4x from both sides. And I can simply add my like terms, which is 10 minus 8, which is 2. And therefore, I get x equals 2. Now, as we look at this problem, we want to be mindful of the fact that really initially when we look at the LCD, we can note that x can't be two numbers. X can't be 0, and x can't be, well, gosh, x can't be 2. So because we happen to get x equals 2 as an answer, this problem doesn't even have a solution. We say no solution to this. And this could very easily happen on a rational equation problem, as we can see. And we can even check our answer to see that we're on track. We can graph the left side of the equation as y1, we can graph the right side of the equation as y2. We will do that in class, but again, this is a no solution problem. Okay, moving on. So the boundary algorithm is obviously popping up here again. Solve the boundary equation, determine test intervals by plotting test points. Obviously that will help. Pick a test point per interval and then test those. And then include the intervals that make the inequality true in a solution. Okay. Okay, so on number 1 here, what we're going to go ahead and do is we're going to reflect upon how we would do this problem if we had done it in Algebra 1, Algebra 2. And then I'm going to take it back to the boundary algorithm and how it relates to that. Initially, I will be subtracting 2 from both sides, simply because I want to isolate the absolute value. And reflecting upon, again, how we would do this in Algebra 1 or Algebra 2. We just rewrite the inequality as such. And we also, of course, on the other side of this, we write less than or equal, we'll say -5 technically. -5 less than or equal to this quantity, which is less than or equal to 5. Okay, so when we go ahead and, as the boundary algorithm suggests, and as I showed on the previous page, we'll set up -5 less than or equal to x minus 3, and x minus 3 is less than or equal to 5. We'll go ahead and add 5 to both sides, so 0 is less than or equal to x plus 2. And if we subtract 5, we'll get x minus 8 is less than or equal to 0. On our number line, we'll have 2 critical values, one at -2, one at 8. At -2, it should be closed. At 8, it should also be closed. And because we want answers that will be, if I read this from right to left, I want values here that are greater than or equal to 0. So let's pick a number that's less than -2. Let's say -3. -3 plus 2 is not greater than or equal to 0. Let's pick a number like 9. Under this inequality, 9 minus 8 is 1, which is not less than or equal to 0. So if we pick a number like 0, it should work for both. In other words, 0 plus 2 is greater than or equal to 0, and 0 minus 8 is less than or equal to 0. So then we write our final answer accordingly. Bracket at -2, bracket at 8, and there's our final answer in interval notation.